All right, so let's see what we want to do with this guy. This guy is going to take two plates that are 400 square centimeters, charge them each to plus or minus 10 nanocoulombs. So the top plate, I wanted to write a 1, is going to be minus 10, and the bottom plate is plus 10. The fields, you'll remember, coming out of these things come up out of the um, positive plate or down out of it. It comes straight out. So below it will go down, above it will go up, and that's perfectly fine. The same or the opposite thing happens with the negatively charged plate, not flate. Um, the field goes into the negatively charged plate. So above it, it'll go down, and below it will go up. So that in between, the fields here are going to add up. Okay, so that's part of the reason why we're using the parallel plates. That makes life pretty easy because you just add the magnitudes to get the field, and it's going to be going upwards. The other reason is because this is a sort of a paradigmatic capacitor. There's something called a parallel plate capacitor. All right, let's see. Parallel plate, right? And it's basically got this design. It's two plates that are a small distance between, or a small distance from each other. You apply a voltage, you put a battery on either side of power supply. That creates a potential difference, and then you get charge stored on the plate. This time, we're not doing that. We don't have any wires connected to it, so it's just two parallel plates. We're going to find that potential difference. That potential difference is, in fact, going to be the exact same as if we put a voltage on here and ended up with these charges. So this is just a little something that will show up a little bit later in the course. So this looks like a capacitor, like that. Oops. All right, so let's see what else can we do with this. So we've got the potential difference between the plates. It's good. Let's see, that is going to be delta V is equal to E times D, where E is unknown. We don't know what that is. We're going to have to find that in part A. Part B, we'll find the delta V, and D we do know, so that's a check mark. That's 5 centimeters. So that doesn't have anything to do with the first part, but it will have something to do with the second part. The second part is going to use the fact that we found in the previous lecture, which was that if you take the charge density on one of these plates and divide it by 2 and then multiply by that constant, that Coulomb constant, which is 1 over 4 pi times the permittivity of free space, then this will give you the field coming out of it. All right, and remember that charge density is Q over A. Q again in this case is 10 nanocoulombs, 10 times 10 to the minus 9 coulombs, and A is 0.2 meters squared, right? 400 square centimeters, 0.2 meters squared is 0.04, 10 times, 4 times 10 to the minus 2 meters squared. Right, so that says sigma is 2.5 times 10 to the minus 7 coulombs per meter squared. Okay, so that tells us what the charge density on each one of these things is. So what do we want to do now? Well, we're going to use superposition, right? And superposition just says that at any point in space, you just add the two fields. So we have a field from this source and we have a field from that source. So we add the fields from all the different sources, which in this case means we add E1 plus E2. They're both actually going to be going upwards. They're going to be positive. So they're both going to be exactly the same because there's no variation here with distance, right? No distance change in here. So that's another reason why we like the parallel plate setup. So we have 1/2 KE, and we'll just take the absolute value of the charge density plus 1/2 KE times the absolute value of the charge density. If in the absolute value, these are both the same, so we can just say that's, well, let's get rid of those guys. We have KE sigma, which is 9 times 10 to the 9th Newton meters squared per Coulomb squared. Okay. Times what we just found it, which was 2.5 times 10 to the minus 7, I hope. Yeah, that looks right. Coulombs per meter squared. Okay, so 2.5 times this is 18 plus 4.5, which is 22.5. So that's 22.5 times 10 to the 9th times 10 to the minus 7th is 10 squared. That's 100. Cancel out 1 Coulomb and the meter squared. So that is newtons per Coulomb. That's right for electric field, so we're doing pretty good. Let's just multiply that 100 by the 22.5, so that's 2250 newtons per Coulomb. All right, so that is the charge, or the field from the charges. Okay, now we need to find the potential difference between the plates. And we'll just use that formula I just intimated earlier, V equals ED. And that is going to just be this 2250 newtons per Coulomb times 0.05 meters. The way to say 0.05 meters is 1/20th of a meter. Okay, so I'm going to divide 2250 by 20. So that gives me 1. I've got another 1. 20, 20. So I have 50 now. 50 divided by 20 is 2. And that gives me a point there. And that leaves me with 100, so 22.5. Newtons times meters over coulombs. Newtons meters over coulombs is something we call a volt. So that's 112.5 volts. Let's see if I agree with myself. I am agreeing with myself, so life is good. So there are lots of little parts of this problem. The things you needed to know were superposition, that you have to be able to add these fields. You need to know the charge density in the field for this thing, the field for the plate. And I could give you this for another field, obviously, so, or something similar. It wouldn't be too much similar to this because I'd have to find some way to keep the field reasonably constant for you because we don't want to do integrals. But you do need to know the fields for the other things. Put those in your notebooks. Remember, notebooks are things that you can use on your tests. Then we've got all this good stuff. We just do math and end up with 2250. That comes in here, as does the 5 centimeters, and you're done, right? This might look familiar. Remember that E is equal to force over Q, the charge, on an object. V is equal to the energy over Q on an object. So this particular equation might look a lot like, if you were thinking about it, work equals force times distance. Change in energy equals force times distance. All right, so that's actually exactly what it is, right? So that's one of the reasons why this voltage, this potential is so useful. All right, that seems like it's enough for now. Maybe we'll go on and do one more problem in a second. All right.